you. Well, I'm glad to see that morale is still high and there are still people in the room. I'm tired too, so I promise to keep the technicalities to the bare minimum and focus in the conceptual aspects of this talk, which in my opinion are the relevant things. So this is the true quantum field theory experts in this work are Bruno and Benito, which you probably know. And well, we decided to come together and mix our expertises. So I guess I'm skipping why to look for Lorentz violation. So let me tell you that. So we know we need to look for a theory of quantum gravity, and most quantum gravity candidates, either fundamentally or at some point in their implementation via truncations or discretization or whatnot, introduce some sort of Lorentz violation, okay? So Lorentz violation can be tied to quantum aspects of gravity. In another area, we have been discussing measurements in quantum mechanics, which seems to happen instantaneously. And this instantaneous structure is non-geometrical and could be additional. So that would be another notion where Lorentz invariance is broken, right? Because we would need a preferred notion of instantaneity. And in addition, we can say that, well, let's simply do physics, okay? We have an hypothesis in relativity, which is called Lorentz invariant, which states that all inertial frames are physically equivalent. So as physicists, we have the duty to go and test this hypothesis, okay? So let's break it and let's see what remains, okay? So these are the kind of motivations we have when we start breaking relativity, if you wish. It's not that we don't understand that relativity is beautiful and powerful, it's that we understand it and we want to test it and quantify how beautiful and how powerful it is, and what happens if we lose this basic principle behind relativity called Lorentz invariance. Okay, so most studies in the literature regarding Lorentz violation are classical. Okay, there are parametrizations as general as possible of Lorentz violation. People take them, work with them, get a Hamiltonian, and then go and compare with the relevant experiment and put bounds in the parameters for Lorentz violation. This is all classical in the mathematical part of it, and the bounds are mind-blowing. But the question is whether quantum mechanics open the door to different kind of tests to Lorentz violation. And in this regard, there are some interesting works. So people have studied how these parameters for Lorentz violation run with energy. Jorma and Bikar Hussein studied Unruh-De Witt detectors for modified dispersion relations with a mass scale that may come from Lorentz violation. There will be a talk here regarding Hawking temperature and Lorentz violation, etc. Okay, so this is just a very simple addition to this list of quantum aspects of Lorentz violation, and I would say we got to a point where we thought that we had Lorentz violation hunted. We had hunted Lorentz violation, and as I will try to convince you, this prey went away when we got to a more realistic point of view. Okay, so we worked with a very particular model, the simplest we could build. So we worked with a scalar field. This is, of course, not part of nature unless, well, you consider the Higgs or whatnot, but this is not like the conventional fields that are used for test of Lorentz violation. So this is a proof of concept work. And this is a conventional Klein-Gordon up to this term C coupled to the kinetic term, where all the new stuff is encoded here by C. So C is going to be a God-given tensor, a non-dynamical tensor, okay? Something that is fixed in space-time, and it doesn't matter what we do, we cannot affect it, okay? So if we switch frames, C doesn't change with us, okay? Because it's attached to space-time, and that's what is breaking relativity. Okay, so in particular, we went even further to simplify the story, and we considered the simplest possible C, which in some Minkowskian coordinates takes this form. Well, this has some names, but this C can be interpreted as a parameter, capital C, times a preferred vector field. So this vector field is giving us a preferred notion of a preferred direction, if you wish, in space-time, or in other words, a preferred foliation, a preferred notion of instantaneities. Okay, so in this sense, we're breaking relativity. Okay, and you may see that there's the preferred time, if you wish, but I can also work in a boosted frame. Okay, and for the boosted frame, well, these errors are not, if you wish, perpendicular to it. Okay, so the physics is different. That's what Lorentz violation is all about. Okay, if I boost, the physics does change. Okay, so what we did is to quantize the scalar field in two frames. First, in the preferred frame, which is, let's say, the orthogonal frame, and then in a boosted frame. Okay, so the quantization carries on as always. Okay, well, I don't even need to go through the details. I think we get the symplectic product. We pick the positive energy modes, whatnot, and we have a complete set of normalized solutions. And then we can repeat the story in the boosted frame. So here, what I did is the same picture, but now I'm drawing this Cauchy surface horizontally. So the notion of preferred time now is tilted. That's this. Okay, so I can repeat the story of quantizing my field in this boosted frame where the physical situation is different. Well, I do exactly the same. And now I can use the technology of Bogoliubov transformations and all that to compare the two vacua, the vacua in one quantization with the vacua in the other. And that's basically what we did. So, well, this is the concrete expression for the beta coefficients. I would like you to notice that whenever capital C goes to 0, namely whenever Lorentz violation is not there, beta goes to 0, and whenever the boost has relative velocity 0, beta goes to 0 as well. Okay, so well, these are two limits that are worth mentioning, but in general, I do have a non-vanishing beta. Okay, so well, conventional story. I would like to see the expectation value of the number operator for the prime system, for the boosted system, in the expectation value of my, in the vacua of my preferred quantization. Okay, and that's basically beta squared, the integral, and this is a function we call kappa times a delta, which comes out of the distribution nature of the objects we're dealing with. The important thing is that we plotted kappa, and kappa is over here, and you may notice, so the two lines had to do with the choice of the mass for my scalar field. So let's focus on the, on the red curve, which is associated with massless fields, just for simplicity. You may see that this is a step function, but it's never 0. Okay, so on the positive axis, I have a given value which goes all the way to infinity, and on the negative part of it, I have a higher value which goes all the way to minus infinity. Okay, so this means that an inertial observer, okay, assuming that the state was prepared in the preferred vacuum, then a boosted inertial observer will see particles of arbitrary high momentum. Okay, So if Lorentz invariance is there, if Lorentz violation is there, excuse me, it seems to be that if we move inertially with respect to the preferred reference frame, we would be burned by particles of arbitrary high momentum. So it seems that there's an enormous tension between breaking Lorentz invariant and quantizing our fields. Okay, so we were very happy that we were killing Lorentz violation. However, well, I have a couple of comments here that may be important. So let me just say, these vacua are not unitarily equivalent. And of course, everybody here is familiar with the Stombo-Newman theorem and the fact that it requires a finite number of degrees of freedom, which we clearly don't have. Okay, so we were very happy, but then we said, okay, we want to actually kill it. So let's put the simplest possible interaction and show that anything moving inertially will fill our particles of arbitrary high momentum. So we studied an Unruh-De Witt detector, and well, we calculated the amplitude for the detector to get excited, and the amplitude is 0. And we did this to all orders in the Dyson series. Okay, so even though it seems to be that if Lorentz is not a symmetry, we would be seeing particles of arbitrary high momentum, there's no way to detect it, at least not through an Unruh-De Witt detector, which is the simplest way to couple to this field. Okay, so let me finish by telling you that, well, what we showed is that in a Lorentz-violating theory, inertial vacua are unitarily inequivalent, okay, which is somehow expected, right? That's breaking Lorentz invariant. Lorentz invariant means equivalence between inertial frames. So if I'm gonna break it, but this goes all the way to the quantum realm by having unitarily inequivalent vacua. Okay, so the concept of the vacua, the vacuum doesn't exist, no, which is in these theories, which is something we read in the books, like of course there's always an inertial vacua, but you have to be careful of this, because in these theories there are many vacua, but they are not unitarily equivalent. Okay, so then we saw that the preferred vacuum seems to be populated by particles of arbitrary high momentum, as seen by inertial observers with respect to the preferred velocity in spacetime. But Unruh-De Witt detectors cannot be excited by this phenomena. Well, this is a very narrow path of what we did. Let me make some comments of what else we went through. So, well, I mentioned this. We actually worked to arbitrary orders in the Dyson series. Let me say that what I mentioned is about the probability of the detector getting excited. The de-excitation of the detector is a different story. There could be effects. Okay, so we could still kill Lorentz violation by looking at spontaneous emission. Okay, but it's a little bit harder phenomenologically. We studied the divergence of the two-point function, and the result in a nutshell. Let me go back to my action. The result in a nutshell is what you expect, that the actual metric that governs the divergence of the two-point function is these two objects put together, which they could be called an effective metric eta tilde. And of course, this is just the first steps into this possibly fruitful line of work. We would need to study realistic fields in the sense of fields of the standard model, which we could use in experiments. They should be the objects that actually describe the objects in the experiments. We could use other ways of violating Lorentz invariance, and in particular, we could we could use space-time dependent ways of violating Lorentz invariance, which they exist, and we have reasons to believe the story would change in some key parts. And we could consider non-inertial trajectories, of course. The point is that there's a lesson for everybody quantizing fields whenever Lorentz invariant is not present. And the lesson is beware, because you may no longer jump from one inertial system to the other as easily as we usually do. Thank you.
Thank you. Any questions? Yes.
Hi, thanks for the nice talk. I have conceptual questions on the way you implemented Lorentz violation. I think it's in relation to the last comments you did on that. There could be other ways, because the term you introduce there in the action, which breaks Lorentz invariance, is it really implementing that, okay, Lorentz invariance is not like within the laws that govern nature, or is it that you're really introducing something physical? So let me put it very graphical. I mean, the room we are here now, it's breaking Lorentz invariance. It's not Lorentz invariant. But the rules that govern the physics in here, in this room, are Lorentz invariant.
Exactly.
So are you really changing the rules, or are you just putting something physical there that it's saying, okay, wait, I mean, I'm doing in theory in presence of something physical that is choosing a preferred reference frame?
See, I get your question. So the most important distinction is to say that Lorentz is a symmetry of the theory and not of the solution. Okay. So this room is already a solution of some theory. Okay. So of course, the particular solution may have preferred directions. Well, of course, no. But that's a preferred direction of a situation. Lorentz is a symmetry of the theory. Okay. So if C were not here and I do an arbitrary variation of my action, I may see that if my fields transform under Lorentz as we know they transform, this is a symmetry. Whenever C is present, this is no longer a symmetry, because C does not transform by assumption, because it's God-given and fixed. Okay, so putting there non-dynamical fields, non-dynamical tensors, makes you break the symmetry of the theory.